At the elevator at 12:30, if you are interested, please come together. And today I'm thinking we can go to an Indian restaurant on the avenue called Shalimar. Actually, we went there once last week as well. And at 3 o'clock in the afternoon, we will have an informal discussion in the conference room C441 and with cookies. And today I would like to invite people to, but not, I will not pay. For dinner to an area called Ballard. We need to go there by bus. It will take us about half an hour to get there by bus. So I'm thinking we can gather at the elevator at 5:30 and go together. And I will need to, at the end of your talk, I will need to count a number of people who want to go to the dinner, because I need to find out how many people we have. Then I may need to make a reservation.
What is the restaurant?
So there are a couple of options. Either there's a Mexican restaurant and also there's a Mediterranean restaurant. The Mexican restaurant is kind of small, so, but the Mediterranean restaurant has more space. So it's not yet decided. Okay. Today I'd like to welcome Nathan Harshman from American University to talk about one-dimensional code atoms in harmonic traps.
Thank you. Thank you for the introduction. Thank you for being here. I think this is recording when flashing. Yeah. So, so again, and thanks for coming to the talk. Sorry, I think, is Artem still sick? Do we know that? That's too bad, because certainly of all the people here, he's the one who I've spoken to the most about this before. I'm sort of new to few body physics, so I welcome you to interrupt me and to say, this is all known. This was known in the 70s by, right? So please do that, because I hope to learn from you as much as I hope to impart you with what I know. Okay, and again, a lot of what I'm going to say, I assume almost all of you know, you just know in a slightly different language. But it's nice to see things we know put in one place all together, neatly organized. All right, so just to make sure what I'm talking about is I am going to be talking mostly about Hamiltonians like this, right? So I have n particles in one dimension. I'm going to assume they all have the same mass throughout almost all the talk. I'm going to say they all feel the same trap. And then there are only two body interactions, right? So a pretty straightforward Hamiltonian. And let me see, if I express the symmetry of this Hamiltonian in the most erudite fashion, it looks like that, right? So I'm saying any trap and any interaction, but I mean one-dimensional, symmetric, spin-independent trap with a one-dimensional Galilean invariant spin-independent interaction. And so this has permutation symmetry. I can change all the x's. It has relative parity. I can, so it has center of mass parity and relative parity. In other words, the total parity is a symmetry of this, but you can also break it into the center of mass and the relative parity. So that's the most general. A lot of what I'm going to say would apply to that, although I'm going to spend most of my talk talking about the even more specific interaction, where and now I've scaled my position variables so everything is nice, where I have a harmonic trap and where I have a contact interaction. I actually don't know why I have those absolute values in there. Cut and paste error. Right, and so then I still have permutation symmetry, I still have relative parity, and now I have even more. I have the center of mass as a harmonic oscillator. And if we want to be, again, as erudite as possible, we say the center of mass has U1 degrees of freedom. Maybe I'll talk more about that. But this has additional symmetries. Now, these additional symmetries it has depend on what this coupling constant interaction strength parameter is. I have the contact symmetry, the transformation symmetry of my Hamiltonian goes all the way to U of n when G is 0. In other words, when I take this out, I have an isotropic harmonic oscillator in n dimensions, and that is a super integrable system with a lot of symmetry, right? And lots of different ways, lots of different coordinate systems one can use to separate the variables and all sorts of fun stuff. Additionally, when either G equals 0 or G goes to infinity, And again, I sort of attribute this to Werner and Castamp, but other people probably said it first, but that's where I read it. This system also has a spectrum generating system, SO21, meaning that I can relate the energy levels in a way that is very familiar to you, and this is just basically a very fancy way of saying that I can separate the angular part from the radial part. Okay, so this is what I'm going to be talking about.
I have a question about your interaction. So the way you've written it there is that you have exactly one G coupling constant.
That is right. That is right.
But sort of looking ahead a little bit, you might be applying it to two-component Fermi systems.
That's right.
And at the same time, you're saying your interactions are spin independent, which would mean that you have to restrict your I and J in some way. So
I see.
does
Yeah,
that
yeah.
mess up your symmetries? Or?
Yeah, so that would reduce the symmetry, right? If these G's aren't the same for all the different components, then that does mess that up. Absolutely. Now again, I say spin, I could be talking about any internal degree of freedom. And so one could imagine, I mean, so yes, that absolutely could mess it up. That's right. And then we'd have to break this. We should still have this and this, but we'd have to break this up. And we'd have to be very careful. Yeah, that's right.
At the moment, if you have, say, two up particles, you would still say they're interacting with the coupling constant G, and then it's the fact that the wave function has to vanish that turns off that interaction.
That's right.
Is that correct?
That's right. That's exactly right. That's exactly right.
I'm also not used to expressing these in terms of this symmetry language. So could you summarize what information is contained in saying this has U1 symmetry? So
I will go into more detail about that. But in summary, so whenever I say a harmonic a couple ways to saying it, right? So I have my creation operator and my annihilation operator. If I make the transformation, A dagger goes to E I theta. So in other words, I have U1 as just unitary one-dimensional matrices, so it's just E to the I theta. This transformation, where that goes to that, leaves my Hamiltonian invariant. So we can call that U1, and then, I mean, these, so again, I recognize that I'm sort of saying things everybody knows in just a slightly different language, but right, these have representations that are characterized by a single quantum number, and that's just the center of mass quantum number. And whereas, right, if we don't have a harmonic oscillator, we only can say something about the parity of the center of mass. But if we have a harmonic trap, that becomes a good quantum number that characterizes the energy entirely.
But that would be true for almost any potential you put. It's not so special to a harmonic oscillator, I wouldn't think.
Oh, it isn't. I mean, it has to be the harmonic, otherwise it doesn't separate out. Otherwise, when you make this rescale, what's the right way to say this? Yeah, it doesn't separate out. This is only true for the harmonic oscillator.
Okay, so this is a statement of separability of center.
Exactly, right? What I mean by that X is this is only acting on the center of mass, this is only and these two are acting on the relative. And I'll show another sort of picture of that again in a second.
What is the relative parity?
So should I go? Maybe I ought to just go to that slide for a second, but then I'll come back to motivation. So I'll go to that slide. So first off, just so you know, I will go to Jacobi coordinates. Here's I actually like to call this Jacobi hypercylindrical, because I still have my center of mass. I'm going to leave as the spine, right? And then rho measures the distance from the spine of the center of mass. So I like to call it not Jacobi hyperspherical, but Jacobi hypercylindrical. So I can make this transformation to these coordinates, and then I could think about how each of these factors acts on it. So the permutation group only acts on R1 through Rn minus 1, only acts on the relative coordinates, and it acts as a matrix, right, that mixes those all up.
Well, it's not that the R is invariant on the permutation?
The rho is invariant.
The rho.
But if I think of these are, for example, R1 is just is the separation between particle 1 and particle 2. R2 is the normal separation between particle 3 and the center of mass of 1 and 2. So these are sort of normal Jacobi coordinates.
Big R is what?
Big R is the center of mass.
Okay, so the center of mass is also invariant over the representation.
That's right. And so if you see, if I pick a particular permutation, I'll mix up my R1 through Rn minus 1, but I leave my R invariant. What I mean by relative parity is the operation that flips all of the R's to minus R's, but it doesn't do anything to the center of mass. And what I mean by the U1 is I can replace R by e to the I theta R. Well, that looks a little fudgy, right? But if we think of this as R dagger R and P dagger P, then that complex conjugate will wash out. So that's what I mean by this way of writing the symmetries, right? This is a representation, an n-1 representation of the permutation group, the standard relative parity, and then the U1, which includes the center of mass parity in it, because I could just pick the right theta.
I think that am I just being an idiot? The center of mass is not invariant under permutations. The mass is different.
That's right. This is only for equal mass. This is only for equal mass. Absolutely. No. So I am doing the equal mass case. Every interaction I am saying is the same, or eventually when we go to the unitary limit, it sometimes doesn't matter because they are so repulsive it doesn't. The nodes are forced to the right places.
Well, but I guess sort of in the language that people might be more used to, you say, if your relative and center of mass motion separates, your wave function is the product, and then you have the total parity is simply the product of the relative parity times the center of mass parity. And if you pick a given relative parity and the center of mass parity, you know your total parity.
That's right.
And I think that would be
A normal.
translating it into wave function language.
Yeah, right. If we think of capital pi as the total parity, then you can and we have a harmonic oscillator state. Since we can separate off the center of mass harmonic oscillator, we know its parity is -1 to its quantum number times then this will be the relative parity. And what we'll see later is that is always -1 to the lambda, where lambda is whatever hyperangular momentum we're worrying about, depending on what dimension we're in, whether it's
So what transformation is that capital R the center of mass position?
capital R is the center of mass.
And then you transform it to a complex number?
That's right. That's right. So you can think of this. So I mean, maybe this is a little fudgy way of writing it. Probably the best way to think about it is this way. These are equivalent. And you could think about then, if I was going to write this not in the position representation, but if I was going to write the center of mass Hamiltonian as 1/2 P R dagger P R plus, yeah, so in normalized coordinates, R dagger R, right? If I retake this operator and multiply it by e to the I theta, then R dagger R is invariant. And the same trick for if I want to preserve my canonical commutation relations, the same phase rotates my PR with a complex conjugate. Does that make sense? So I am going to try to claim, so I'm glad we are spending time to make sure that this makes sense. And I think it will make more sense. I'm going to show a bunch of pictures, and I'm hoping that'll make this make a lot more sense. So maybe I shouldn't have started with the most formal way of writing it. But let me go back at least for a second and tell you what I'm going to do. So I'm going to try to make that symmetry make sense by showing a bunch of pictures of wave functions configuration space. And then I'm going to show, once I've convinced you that that makes sense, that is useful for doing a spectroscopic classification of the states in the same way that when we classify normal electronic states, we classify them by their irreducible representations of their symmetry groups. That this is just the normal way we do spectroscopy. And then at the very end, I'll tell you my secret motivation. But first, my public motivation. So Right, so mathematical physics. This Hamiltonian and things of this variety have been studied extensively since the 60s. These are some of the touchstones of mathematical physics, right? I mean, related to this are Liebleiniger and Girardot and all of these kind of models, which were sort of how do we start making integrable, solvable, many particle models, and as a result, people have studied them for a long time. And what we know is that there's this deep connection between symmetry and integrability. Of course, more recently, this model and related models have been shown, have been useful for studying universality in few-body physics, right? And especially, is it Joachim? Is that how you say it? The Joachim experiments where they're doing multi-component fermions and effectively one-dimensional traps, and lots of other people there's been a flurry of papers on this particular model in the last few years. And really sustained interest for longer than that. So that's of course why I'm here and why I'm learning so much from all of you. Again, maybe more generally, is when I like using symmetry methods, and I see this as a great example of where you can use the power of symmetry. I always joke that whenever somebody's doing an exact diagonalization method and there's a zero matrix element, then I have failed. Right? Because if you are exploiting all the possible symmetries, there should not be any zero matrix elements, right? Because that indicates that there is some symmetry that you have, if you've had to calculate that and you got zero, you've missed a symmetry. So I am here, right, trying to get rid of all the zeros. Also, again, when you think about then, dynamically changing G, either slowly or quickly, that process is symmetry conserving also, right? So you don't suddenly explode into all of the Hilbert space. You still stay in the sectors of the Hilbert space with the same symmetry. And so one can imagine either using this to help calculations or using this to use these symmetry principles to make sure you get to the right, you map to the right state when you're trying to control the system. But also, symmetry has limits. And the more degrees of freedom you have, the less constraining the symmetry becomes, as well as the more difficult it actually becomes to implement the symmetry, right? And so I'm really interested in trying to figure out, right, so where is the trade-off in which symmetry methods don't give you enough, right? And is that just a calculational limit? And if we were cleverer with better analytic computers, we could overcome that. Or is it really a failure that as you go to more degrees of freedom, the symmetry really becomes less useful, right? And you get this sort of emergent complexity of many body systems that's different from few body systems. So that's the high level motivation for all this. Okay. So I just showed you this, right? So I will be using Jacobi hypercylindrical coordinates throughout. There's the different versions depending on how you like to normalize things, but I'm doing equal mass. Yeah. And so then when you do that, you can think of each of these factors as acting on the configuration space, as on our n-dimensional configuration space. Okay, so what does that actually mean, though? Well, so let's look at the simplest case. That's always a good place to start. Let's look at two-particle configuration space. And what we know then, right, is that we could draw this line, the line where R1, the separation, is equal to 0, and that divides our configuration space into particle 2 on the left, particle 2 on the right, right? And so we can just divide that up. And then we can draw another axis corresponding to our center of mass is 0. Well, so I look at this, and I say to myself, okay, how do I geometrize these kinds of symmetries here? So S2, so that's exchanging the two particles. If I exchange particles 1 and 2, what that's like is reflecting over this axis. Did I say that right? No, I said it exactly wrong. It's like reflecting over this axis, right? So, and then if I want to, and then we know in 2 dimensions, a total parity would be rotating by 180 degrees. I'll use sort of standard kind of chemical notation or chemical physics, quantum chemistry notation C2. So yeah, I have these exactly labeled wrong. Haha. And then we can also imagine inverting the parity and changing the particles, and that would be reflection around that axis, right? So now again, if we had different mass particles, we wouldn't have as much symmetry because we couldn't exchange the two particles, right? One could imagine doing some sort of transformation that might make these two orthogonal again, so we'd get back to that symmetry, but then you'd end up deforming your equipotentials in such a way that would make that problem hard to solve, right? Or you might be able to solve some problem, but you're gonna lose somewhere. Something's gonna go wrong. Maybe this line will become curved, right? And so this is the line where the particles are on top of each other, the coincidence line.
So why did you include the trivial U1 before but not here?
Because I'm just talking about configuration space, and I haven't even added in the fact that I haven't put my equipotential in here, right? I could put my equipotentials in here, and then we'd see it. Good. We're going to look at 3-particle configuration space. So again, so here's the particle coordinates. Again, it's always sort of hard to see this view. This pink disk is like the relative plane, and the center of mass is the axis coming out the middle of it. These green structures are the coincidence planes. Those are the loci in configuration space where the particles are on top of each other. The weird little blue marble in the middle, that's just one equipotential of my harmonic oscillator, of my 3-dimensional harmonic oscillator potential. If you look at this has the same symmetry of a hexagonal prism. That's called D6H. I'll go into more detail on that in a second, but of course it's easier if we just go to the relative plane. And so for most of the rest of this talk, I'm just going to leave the center of mass behind.
So, from group theory, right, you can find these isomorphisms.
That's right.
You don't need really to do this geometrical analysis.
That's absolutely right.
Trying to be nice with us.
Well, and I actually found that I couldn't do the math until I had the picture. And that's why I will show results here for 3 and 4 particles, and I'll show some math for 5 particles, but I won't have any pictures, and I won't be able to say clever things, right? I believe that the pictures help, right?
Sure.
I believe it's more than just advertisement.
Yeah, I'm just trying to say that there is
Oh, yeah.
rigorous way.
Oh, absolutely.
You can
Yeah.
also do that.
This has 6 elements, this has 2, this has 2. We take the product, this is a 24. It's isomorphic to this. But
you still have to prove that it's
that's right.
isomorphic.
That's right. And all of that.
The number of operations.
That's right. That's absolutely right. And so, that's right. If we
What is the D6H?
So D6 is the dihedral group with 6 reflection axes and 1 horizontal reflection plane. So it is the same, as if I draw this. And so I can, this is a 6-fold rotation axis. I've got that. I can also reflect along the plane that cuts it in the middle. And then I can also, I have a 2-fold rotation axis around each one of the middle of those faces. And so the 2-fold rotation, the D6 is what you get if you, if you color this in some certain way, and then if you add the horizontal reflection plane, you get D6H. And so there's probably benzene has this same symmetry, right? And so if you look up in a quantum chemistry book, you can classify the electronic states of benzene based on its D6H symmetry. And you can look up on a table what all the representations are and the character groups and all that. And I'm not really going to show any of that machinery in the talk, right? But this is this whole machinery of discrete groups that I'm trying to argue is a really interesting. I'm trying to decide how helpful it is. It seems to be incredibly helpful in 1 dimension, right? It really seems to basically almost totally reduce the problem. It doesn't do it in 2. And I'm not going to talk about that because I don't have anything intelligent to say, but I know it doesn't do it in 2, but I don't know how bad it fails or how useful it could be partially. So if we take out the center of mass degree of freedom and just look at that pink plane, we have the snowflake symmetry, C6V, which we can even classify we can go down all the way down to, so again, relative parity or relative inversion is a rotation by 180 degrees. We can, exchanging two particles are reflections about each of those axes. And so you sort of see how this works, right? Like if I reflect around this axis, this sector, which corresponds to 3, 2, 1, if I exchange 1 and 2, becomes 3, 1, 2. And similarly, if I do parity, right? If I do a 180-degree rotation, it's hard to see. This says 2, 3, 1. Rotate by 180 degrees, it becomes 1, 3, 2. You can also do a combination of a reflection of two reflection, or I guess, yeah, well, parity inversion and an exchange, right? And that corresponds to reflection along these other kinds of lines. Note, for example, this sector is invariant under this operation because switching 2 and 3 and then reversing the parity doesn't change that sector. And so that's sort of, it turns out when you do the actual math of these things, those end up playing an outsized role in the math in terms of classifying things, is which sectors are invariant under classes of operations.
So, for the S3, right, you need just, it has just 2 generators, right?
That's right. You can generate all of S3 from any 2 of those.
So,
And then if you want S3 cross O1, you have to add an inversion. So there are 6. So the identity, these exchanges, and these, that gives you the 6 normal exchanges, and then you also can double it by doing any of those 6 with a parity inversion. Okay. So yeah, and again, I'm just talking about configuration space. If we are doing a harmonic potential, right, then my equipotentials are circles, and of course that's reflected by everything. If it's any other potential, my equipotentials are not circles that will respect this symmetry. Am I saying that right? Yes. They may, my relative potential may, but it won't accept my separation between center of mass and relative. So for example, I could do R to the 4th, but then it wouldn't separate, and I'd have to worry about center of mass. Okay, so let's do 4 particles just to see how it looks. In this diagram, right, so we take the center of mass out, so this is just the relative coordinates. These are sort of orange disks. Those are the 2-particle coincidence disks. Though that loci of points is where 2 particles are on top of each other. You see that 3 of them overlap at these red axes. So you can either, those are, if this has, so this has octahedral symmetry, the same symmetry as a cube. This is the same symmetry as a cube. These red ones are like the body diagonals, and they correspond, right? So I have 3 of those coincidence planes intersecting, so that's a 3-1 cluster. This is the 3-1 cluster, maybe where particle 1 is here and 2, 3, 4 are all at the same place. And this one is particle 2's here and 1, 3, 4 are all in the same place. The face diagonals are the blue ones. Those diagonals are where 2 coincidence planes intersect. So this might be the 1, 2 plane and the 3, 4 plane. So the blue axes are 2, 2 clusters. And then the green ones are 1, 2, 1. You've got a 1, 2 particle, and then the other, so 1, 2 are here, and then 3 and 4 are symmetrically placed. So that's fun, right? And then you have all of this. You can then, so this is a group that has 48 elements, 48 possible discrete transformations, depending on particle exchanges. That'll give you 24. I've just drawn some characteristic ones. For example, there are 6 2-particle reflections, corresponding reflection around each of these 6 disks, et cetera, et cetera. I mean, this is a lot to take in, so let's just sort of let it go. But you see that this is sort of fun. It's very fun. And I had a student who made a model of a cube. We had, because we kept rotating a cube and trying to do this, he went to a wood shop. Anyway, because it was hard to figure this out until you really did it. Okay, so that's, right, so we have that symmetry. And I can't draw that picture. I mean, but it's classified. Coxeter classified all these things. It's called like 3, 2, 3 plus in some sort of scheme. But it's the same. So if you notice, if we go back here, this is the same symmetry as a triangle superposed with an inverted triangle, right? A Star of David has snowflake symmetry, meaning the triangle has S3 symmetry. I add inversion, I get another triangle. This structure has C6V. A cube is actually 2 superposed tetrahedrons, right? And so then this would be 2 superposed, do you know the word? I love words. Pentachoron is the most common. Some people call it a 5-cell. That's terrible. Who wants to call it a 5-cell? I like pentachoron, 5 volume, right? Just like a tetrahedron, 4 shapes, pentachoron. Anyway, so this kind of stuff is a wiki black hole, right? Just fall into Wikipedia and you can spend days wandering through 5-dimensional regular polyhedra. Don't do it unless you...
Where do we get to duodecahedron?
We don't get to duodecahedron today. I mean, yeah, at least I have not come up with a duodecahedron in any of this. I'm sorry. Although, I bet that there are some, for this structure, I bet there are some projections that have that symmetry. But we'd have to ask a geometer.
So what is your motivation in mapping the geometry of the space configuration? Are you looking for hidden symmetries based on the geometry? Or?
So that's a good point. I actually am. There is at least one question that I'm hoping I can solve by looking at this from a geometrical perspective, and I'll get to that in just a second. More generally, it's that, right, so now I'm going to start...
For me, the power of group theory, right, is...
That you don't have to do any of that. Yeah.
Although, so that, but I don't know.
Yeah, well, that's absolutely right, and I'll show you. I mean, I like the pictures, but you're absolutely right. I can do this for 5 particles without having to do any pictures. Right? I can do it for 5 particles. It's harder, but it's not at all prohibitive, right? And I don't have much experience with numerical methods, and I'm certain someone who knows how to do this would do it much faster and better, right? So it's just that it's nice to do it by. It's not if you want to do anything by hand, it's nice to have a picture. So okay, so why am I doing all of this though? Is as you're saying, the real point is I want to classify my states. Because the gift of symmetry is that then you can classify all of your states with respect to their symmetry, and you know that if they're from different symmetries, they won't have any matrix elements, and you know you can have shortcuts to find transformation coefficients and all the whole sort of machinery of why group theory makes quantum mechanics simpler. So here's the big idea. If I have these 3 symmetries, associated with each of these symmetries is an irreducible representation, is a family of irreducible representations. But let us just, for now, call them quantum numbers, and really we don't lose anything by saying that. So I'm going to write my quantum numbers this way. First, I'll write the U1 quantum number. Well, the U1 quantum number is just the center of max excitation number. There's no difference there. That's just the fanciest way of saying it. We have the symmetric group irreducible representation. Now probably, there's 2 sort of notations for these, and so let me just flip to a screen that shows you that in a second, then I'll come back to this. Right, so for the low dimensional, right, so Young tableau, right, so S2, so this is S2, there are 2 irreducible representations, there's a sort of a rules for how you count boxes, and so this means in this vector, particles 1 and 2 are symmetrized. In this irreducible representation, particles 1 and 2 are anti-symmetrized. For S3, you have 2 different irreps. One is totally symmetric, one is totally anti-symmetric, and then you have 2 with partial symmetry. And you could think of, I screwed up, right? This should be 1, 2, 3, and this should be 1, 3, 2. And so you should think about this one as though particle 1 and 2 are symmetric, and 3 is antisymmetric with respect to it, and this one should be 1 and 2 are antisymmetric, and 3 is symmetric to 1. And these are orthogonal. If you construct these vectors, they're orthogonal.
Can you call those partial symmetry?
Yeah, I would call them, if we
I would say mixed symmetry.
mixed symmetry. That's right. I like that even better. I agree with that. What should you say? Just so you sort of follow the talk, right? For 4, right, the number of boxes has to equal 4. So, right, so we have all the partitions of the integer 4 are 4, 3, 1, 2, 2, 2, 1, 1, and 1, 1, 1, 1. You have an irreducible representation for each one and a pattern of symmetry. I am not going to teach you Young tableau right now. That is something, it's fun, right, but it's also, it takes a while, and and you get sort of, I think you get enough of the impression, right, from this that, for example, say I want to have particle 1 and 2 be symmetrically related. Well, I have one possibility here, one possibility here, 2 possibilities here, and 1 possibility here for particles 1 and 2 to have a symmetric relation. Right, so you can play these kinds of games, and that clearly will be helpful when we're trying to symmetrize and anti-symmetrize identical particles. So that's the irreducible representation for Sn. I have the quantum number for the relative parity. And again, as we said before, I could get the total parity from nr and pi. Now, there's not just going to be one appearance of this combination. There's going to be a tower of them, which I will label by tau. I mean, in the same way when you have, when you look at just the one-dimensional harmonic oscillator, you have a tower of even parity and a tower of odd parity. And so you could label your odd parity states 0, 1, 2, 3, and your even parity states 0, 1, 2, 3. So that's what tau stands for. And I just tells you if you have a multi-dimensional representation, I just tells you which vector. So, for example, if I have a 3-dimensional representation, I would be 1, 2, or 3. So I claim this is a complete spectroscopic notation for all states of this problem. That whenever you see these lines where people have calculated the one-dimensional spectrum, you can identify, and I'll show you one of those, each line with one set of quantum numbers uniquely. Up to the degeneracy I should say. Or another way to say this is each one of these is going to have an energy that only depends on these. And it doesn't matter what G is. And as I tune G, this energy will change. But tau, its ordering, isn't going to change. You can't have crossings, because if 2 lines crossed, then at that value of G, there would be some other symmetry. And so that means that in our Hamiltonian we're considering, there'd be magical values of G. I have not proven there are not magical values of G. I believe, though, I am right nonetheless. I've talked to Artem about this. Artem has sort of a strategy for maybe how he would want to do this. And I'd like to see this proof clearly made that there are no other symmetries.
Maybe in 1D, but I mean, like with molecules, like
Oh, yeah.
states have conical intersections that I think are not symmetry related. I mean, in addition to the ones that, like Young
Right.
that are symmetry related.
Oh, okay. Okay. Well, so I believe that, and I believe it also depends very strongly on the specific interactions, right? Because in fact, I'm sort of lying because these energies are not distinct when you either have non-interacting or the unitarity limit. Then they actually do recoincide, and I'll try to show a figure of that. How am I doing on time? So for what I'm going to show next, I'm usually just going to quote X. So if you think of X as just the relative excitation, I'm going to extract out the center of mass excitation and our sort of 0 point whatever, and just talk about X. So let me show you some examples. I'll start with 3 particles. These are all well known, slightly a different way of doing it, right? But these are all very well known, and various people in here I have seen do this. Should I want to say this? Because I'm sort of looking at the time, and I don't want to go too long. Again, I'm going to also exploit the fact that if you set G equal to 0, you have the same symmetry as an isotropic harmonic oscillator. So you've got more symmetry, so you're going to have additional degeneracies. And additionally, I have this, so SO21, I have a dilation. It's not a dilation invariance. Dilation, meaning changing the length scale, does change the energy because of the harmonic oscillator trap, but it changes the energy in a totally regular way. If you and that regularity can be exploited in quantum mechanics, and it basically just says that when I'm at either of these two limits, zero interaction or unitarity, the total excitation can be characterized by the hyperangular momentum plus 2 times the radial quantum number. I mean, this is the standard result that people know from the isotropic harmonic oscillator. And you can use this formulation from 0 through n dimensions. I mean, it works in all of those. It's a little cleverer in different places. But it also works when you are at the infinite limit where all these sectors are totally disconnected. The length scale given to you by the interaction, if the interaction is infinitely big, it sort of drops out, right? It doesn't affect. The difference is you don't have all possible lambda anymore. You have a much smaller set of possible hyperangular momentas. Okay, so let me show you some pictures. So 3 particles. First, no interactions. These are the lowest energy states with, I'm only drawing the relative plane, so there's no NR. I'm saying there's 0 hyperradial nodes, right? And there's only 1 when lambda is equal to 0. You could think of lambda here as how much angular momentum it has in the perpendicular direction. And these states break up neatly into, so in other words, there's like 2 states with lambda equal 2, and one superposition looks like that, and one superposition looks like that, and it has this mixed symmetry. And you can even say which states can have those, right? So this is totally symmetric, so that's the 3 bosons. This one is totally antisymmetric, so that's the first fermion state. That's the first odd parity bosonic state. And these could be mixed. These are the two bosons and something else, 2 fermions and something else. So what we do is we take this one, right? We do the standard Girardot trick, and we can take this one, which I've now recolored, so you can more clearly see warm colors positive, cool colors negative. And I could take each of those independent sectors and build the Girardot state. So right, that uses, these 2 states have exactly the same energy because these boundaries are impenetrable. And so this is just the bosonic one. I can also use these to make the fermionics and the bosonics with the negative parity and the positive parity. And so notice again, even though this has negative parity, you can make positive parity states out of it. And again, remember just to see in parity in this, you can tell it's positive parity because I can rotate it by 180 degrees and I get back to the same thing. Whereas these, I rotate by 180 degrees, I don't get back to the same thing.
When you say Girardot state, are you talking about fermionization?
Exactly, right? So this is the magnitude of that. This state is exactly the magnitude of that state.
That doesn't obey the boundary conditions, unless you have delta function.
That's exactly right. I'm only doing the contact interaction, and it is exactly 0 on all of the axes.
You have contact interaction.
I have contact interactions. I'm still, and all of this at the unitary limit. Now that's a good point, right? If this was not a contact interaction, this would be a higher energy state because there would be there would be a matrix element there.
It's not even allowed. I mean, it doesn't have continuous derivatives.
Right.
It's not even
Yeah.
in the Hilbert state.
Yeah, so I mean, but the similar kind of state, right, would look something like that. In the unitary limit of, for example, something that had a non-zero effective range would look something like this, but it wouldn't be. All of these 6 states have the same energy. And yeah.
So,
Yep.
like just mixing 2 states, right? So if the, let's say the spatial part is mixed symmetry, right? That that means to me that the spin part also has to be mixed symmetry, so you can actually get a fully symmetric.
That's right. Absolutely true.
So that for me it was always a thing. How do you prepare these states?
Right.
By the typical experiments, right? They have all atoms in, or the bosonic in this complete fully symmetric or full antisymmetric. How do you prepare?
So the preparation question is something that is hard for me to say what the right answer is, right? But I'll tell you, the state with this symmetry, if I had a two-component fermion and I had tuned the interaction strength tuned so it was at the unitary limit, this would be the lowest energy state. And so whatever kind of cooling I did, this would be its spatial state, and its spins would arrange itself so that it had the right combination of spins so that this was its ground state, right? I mean, as long as I can get it to the ground state, then it will have this spatial state. I mean, I have a slide on this in a second, so maybe I'll go to that and say more about how to combine it with the spin, because you're right, these are just the spatial states. And so then you do have to combine that with the spin states, which themselves can be symmetrized or antisymmetrized or mixed symmetrized. Lieb-Mattis. That's Lieb-Mattis theorem sort of tells you how to find the ground state. Do you know the I think it's, there's a name for these things. Yeah, so Lieb-Mattis is in solid state, or in the condensed matter community, you just say Lieb-Mattis, and you just walk out of the room. You just walk out. So just to make the argument right is that, so this is the energy hierarchy, right? In the non-interacting limit, this has the lowest energy, next higher, next higher, next higher. If you go to the, and they have these qualifications or these classifications, when you map, if you slowly tuned, they map 1-to-1 to those states. And you can show that you have a band like this, a 6-fold degenerate band, for any lambda that is 3 plus 6 times an integer will have this decomposition, and any lambda that is an even number, 6 plus 6k, will have this decomposition. So you have these bands of 6-fold degenerate states, the unitary limit, whose state content is uniquely specified by basically entirely by the symmetry. All you have to know is what are the right lambdas. And for a harmonic oscillator, these lambdas are integers. If this was some other kind of trapping potential, you have this exact same structure, but lambda is not an integer. It's some complicated thing that depends exactly on what the trap shape is and how the energies line up. And that also sort of mangles the adiabatic mapping in the 4-body case and higher, but not in the 3-body case. Yeah, and so I wish I knew more about how to do this. This is just sort of using this. Like if you then try to do, for example, exact diagonalization of just the 3 plus states, you can go up to x max of 30. You only need 40 states. And this is what for all G the spectrum looks like. These are the lowest 40 states. The red lines. So I don't know anything about how to do this, probably a much better way to do this, but you still at least get the right idea, right? Here is the ground state that is the trimer, and then here are these are the dimer states, and you have the Girardot states, and the super Tonks Girardot states over there. And you can get, so this is pretty good fidelity without having to go to that many states. But this is also all well known, so it's not really a new result. It's just sort of a proof of principle.
Don't you expect this energy levels to be equally separated by the atom-dimer excitation?
So I'm not certain they aren't.
Yeah, but the one splitter on that side.
Oh, right. Well, so this is
looks like they are.
right. So first off, yeah, if I had, I don't know how much of that is I assume it's all just that I had to put some cutoff in, and I've just put the cutoff in at a maximum excitation. I haven't done any sort of cleverness to make sure that what I've cut off has been accounted for in some clever fashion. I've just, right, I asked you once about this, like I sort of think of this as the same thing as, well, it's not Gibbs, because it depends, like it gets smaller, this gets better and better.
But you're using the non-interacting basis, right?
That's right. I'm just
So
using
there's no way you could, I mean, it would be non-uniform convergent to describe the zero derivative boundary condition. You know,
Oh.
the finite. But I guess at g equals infinity, it's like the zero derivative.
Right. Okay.
Even it might be just like
Non-uniformly convergent. That is a nice way to say what. Yeah. Okay. That's the technical name for this not working.
It's like the Gibbs phenomenon.
Yeah. Yeah. Okay.
What is not working? Could you repeat the question?
I mean, technically, what I would want to see in this graph is that all of these lines are below the red thing, below the Fermi, the corresponding Fermi state. The red lines are the Fermi states, which are invariant as I tune G, are the totally antisymmetric states. And I would want them to be below them because I'm not at G equals infinity, and I'd want them to converge to them nicely.
You overshoot.
But I overshoot them, and I overshoot them at finite values of G, and I can make that go out further and further, the more basis states I have. And then I have this sort of cascading thing here, and the scale of these cascades, these are all avoided crossings. These are all avoided crossings, but that also changes as I go up in X max, and of course I have all these states which are just flying off into space. So I don't know very much about the mathematics of exact diagonalization, but the point is this is really easy. This basis is pretty good for this. So let's just, in the time remaining, let's say a few things about four particles, just because the pictures are pretty. So just to say this again, so even though now I'm four particles, I can still write in the non-interacting limit, I still have a radial quantum number and a hyperangular quantum number. This tells me how many states have that excitation. That you can get from the UN symmetry, or in this case, the U4 symmetry. U3. Well, anyway, yeah, U3. This tells you how many states have a given lambda. Well, that's just, we're in 3 dimensions, so it's just 2 lambda plus 1. Those are just, so I'm going to use mu to represent the magnetic quantum number. And again, the relative parity is just -1 to lambda, like we always have. So the lowest totally symmetric state, well, that's just lambda equals 0. And we see that we have an even distribution of 4 particle configurations. The next even parity totally symmetric state looks like that. And so these are called the tetrahedral harmonics, and they have been studied in chemistry because they were used for methane and stuff like that. Although, yeah, so these have been seen before. I love this one though, right? This one has primary lobes or primary maxima at the 2-2 clustering and secondary maxima at the 3-1 clustering. And then the next one is lambda equals 6. And it has primary lobes at 3-1, secondary lobes at 1-2-1, and tertiary lobes at 2-2, right? So just these harmonics are tailored to particular patterns of clustering. And remember, when we go up in lambda, we're just adding nodal planes, right? So no nodal planes, spherically symmetric. The next way you can make something be totally symmetric and positive parity is you have to have 4 nodal planes. And then you can get up to 6 nodal planes, and it looks like this.
Nate,
Yep.
In the lambda equals 0 picture, the planes that you've drawn that cut through the sphere, those are the coincidences?
Those are the coincidence planes. And this is the non-interacting case.
So if I were to just, if I could somehow solve the Schrödinger equation in just one of those regions, I would get, with the appropriate boundary conditions at the boundaries, I would get the corresponding spectrum that you're looking for.
Right. And so those are the totally, and those states that solve it with the right boundary condition in the unitary limit are the totally antisymmetric states. Because it has to be, each of these are reflection planes, and you have to, when you exchange 2 particles, it has to go from positive to negative, so it has to go through 0 if you're in the totally antisymmetric spatial state. And the first time you can do that is when you have lambda equals 6, when there are 6 nodal planes, but that's just 0 plus 1 plus 2 plus 3. In other words, that's just the normal Slater, I mean, that's what you'd also get by counting particle excitations in the Slater determinant, right? The first time you can make something that has the right symmetry is when you have a linear combination of 4 different spatial states. Yeah, This doesn't exactly look right because some of these lobes are actually negative, so I sort of just drew this to see the picture here. So you can see this this looks symmetric, but it is antisymmetric. You can see if you sort of if you unwrap the surface. Calculating these coefficients, I do not have an efficient method for, but I can do, right? I can do it, but I know there must be a more clever way of calculating which magnetic quantum numbers in the lambda 6 hyperspherical basis have the right antisymmetry. There must be a clever way of doing that, and it's probably was solved by somebody, by Moshinsky in the 60s, but I just haven't found it yet. So your question is spin. So, for example, here I've done the reduction for all the lambda for the non-interacting case. And so we see, for example, we get antisymmetric states when lambda is 6, the next one is 9, then 10, then 12, then 13. And from each one of those, I can build that lineup at the unitarity limit. But again, most of these have some sort of mixed symmetry. So what can you do? I've just been looking at the spatial Hilbert space. I want to add in the spin Hilbert space. So then I can use this. I mean, if I want to do it this way, I can then use the Young tableau also to make, for example, for 4 particles, there are 2 states with s equals 0. And they correspond to this kind of symmetrization of the particles. This is a 2-dimensional irrep, so both of those kinds of things have spin, total spin 0, sz 0. And here, if I want s2 total spin minus 1, I have this single state, right? There's a game for this, Scherweil decomposition. There's names for these things. And you can use that then to say, if I'm in this irrep, what kind of system can it represent? So for example, say I want a 2-component fermion with 3 up and 1 down, or 3 down and 1 up. Well, I have to have a spatial state that either has this symmetry or this symmetry. And I'll have one of these 3 states I can match with it and do some more machinery and get the right state. I can build the states. And the fact that this goes like that, that's again called the Lieb-Mattis theorem, which is that as you go out to lower total spin, you can shift more of the antisymmetry to between the spin and the spatial. That was not particularly clear, but you can put it all together and you can say, oh, if I want 3, 1 fermions, 2-component fermions, then I should have one of them when lambda's in the 3 space, 4, right? Here's my tower. Here's my degeneracies. Yeah, and so then you can use then, whenever you have a fermionic state, you can use that to make the, right? So each one of these then corresponds to a 24-fold degenerate subspace in the unitary limit that has all possible mixed symmetries. This state can be conveniently represented like this, where each one of these little triangles corresponds to one of these triangles. I've just projected the cube, front of the cube and back of the cube. And you can think of each one of these sectors corresponds to a particular ordering of the 4 particles. And so you see, if this triangle to this triangle, I'm switching 2, 3. Over here, I flip sign. And any 2-particle exchange, I'm crossing one of these blue boundaries. And so whenever I cross a blue boundary, or any boundary over here, I do this. This is the Girardot state. I just put them all pluses. There's mixed symmetry states. In fact, here's the decomposition for lambda even, lambda odd. I mean, you can make all these states. These all states, right? If I had, so these 4 states are useful for positive parity 2-component fermions. The difference when you get to 4 is that sometimes, like this, I have 2 copies of this state. So I have 2 copies of a state with the exact same quantum number. That means there is some mystery symmetry, because if I have two exact copies of the same irreducible representation, there's some other symmetry that I have not identified yet. There's a missing quantum number that's only good, I think, at the unitary limit. Artem claims that quantum number is potential dependent, and I think he's wrong, but every single time I talk to him, he convinces me for about a half an hour before I walk off and think on my own.
Actually, speaking of that, I'm kind of curious about a dynamical issue that I wonder if your method can identify and connect symmetry, which is the fact that surprised me about three-body recombination, which is exactly 0 for a delta function potential in one dimension, but is not 0 if you have finite range
Okay.
dimensions. Have you thought about that and
So-
see whether there is a symmetry difference that will tell you that? I mean, I know now how to understand that kinematically after like Nirov's work when he was in my group, but I would be curious to see if you can see it just from these symmetry.
I would like to think about interactions with range, because it does, what you lose is you keep all the parity and you keep all the permutation, but you lose the SO2-1 symmetry. You lose that which prevents a whole bunch of matrix elements from happening. And so I'm assuming it's somehow related to the breaking of the dilation symmetry. That extra length scale means that there were some 0 matrix elements that are no longer 0. But I'd like to think about that. I think that's right. And what's really fun, right, is that so 3 particles in 1 dimension has the same, the intrinsic 3-body interaction of 3 particles in 1 dimension can be mapped onto 2 particles in 2 dimensions, right? There's all sorts of dimensional regularities where the configuration space is superficially isomorphic, but they have different symmetries imposed. And so I think there's some really fun stuff that could be done there, and interesting, and hopefully intuition.
Related to this question is the fact that even with 0 range interactions, if you let the interactions be multi-channel, you have a multi-channel 0 range, a 2-channel 0 range interaction. Yurovsky and co-workers showed that also gives you a 3-body recombination of non-zero concentration. So it breaks the integrability.
The 0 range multi-channel implicitly includes an effective range term. The phase shift that you get in the 2-channel model, you will have effective range.
Yeah, but it's curious. I wonder if like there's some sort of, I mean, I don't know how that would show up in the symmetry arguments. There's some additional internal
Right, okay.
state which is there, and
Okay,
that
right. I mean, so you could just add another.
symmetry
Okay.
in some way. I don't know. it'd be-
Oh, nice. Yeah, yeah. So I haven't thought about multi-channel at all either. So that would be interesting to think about. Just to give you a schematic again, this is what the adiabatic mapping looks like. If you think of these are the non-interacting limit, these are the lowest states with a certain angular momentum. This is the tower above them as you go up in radial number. You have the same towering structure over here, but these, every time there's a fermionic state over here, you get a 24-dimensional band over here. And this is roughly what the mapping looks like. There's actually still a couple open questions here, so I would not trust this yet, because technically this quantum number, the radial quantum number, should not be conserved by the interaction. And I sort of assumed that when I made this map. I've always mapped, all the bright ones are n rho equals 0. And I don't have a proof that that's how they should map. So you can do this for 5. I won't say anything about it. I mean, you can do the math. You can't draw the pictures, but you can do all the math. It gets harder. They're less simply reducible. And so the sort of what I'm wondering about is is this getting harder, the signature of something interesting, right? S5, the symmetry group here, is a much more complicated group. It's non-solvable, it's not simply reducible, and it has a bunch of other sort of weird properties. S6, even crazier, right? As you go up, the groups become more wild structures. And is that why this method becomes less and less useful? Or will it still be just as useful, just a little bit harder to do? And so I'm interested in that question. Yeah? And one of the key things I need to do is I need to find a more efficient state construction method when you go up in symmetry. That gets a lot harder. So I'm sorry I've gone a little over. I'll just blow through. Again, I was trained as a particle physicist. Then I've been doing quantum information theory. So somehow the reason I'm actually working on this is because I think there is a really deep and interesting connection between integrability, separability. I mean, we sort of use integrability and separability much the same way. We use those words the same way when we talk about quantum mechanics. But we also use separability when we talk about entanglement, right? I mean, that is when something is not entangled, it's because its wave function can be separated between those different particles. So I've done a lot of work looking at entanglement in particle systems, not in qubits. Plenty of people are looking at qubits, but when you actually try to look at a particle and you say, I've got momentum and I've got spin, can the spin be entangled with the momentum? I've got two particles, can the momentum of this one be entangled with the spin of that one? And what are all the possibilities, and which of them are symmetry invariant and which of them are dynamically invariant? And can I always find some observables that separate the system? Because it turns out what you mean by entanglement depends on what observables you can measure and detect, and whether they close. It's called Zanardi's theorem. Is how you separate your Hilbert space depends on what your complete set of observables are. So that's actually what led me to three bodies, is because what you find is in the two-particle case, center of mass and relative coordinates are really useful. And in the two-particle case, you make that separation, and that's complete. And every two-particle problem is integrable and separable in that sense. It's not true for the three-particle case. It might be true for the one-dimensional case, but it's definitely not true in the 2 and 3 dimensions. So the question is can this be inverted, and you can actually use entanglement to say something meaningful about few-body physics? And then maybe, right, if we're thinking about few-body systems as the working material for quantum processors of some sort, well, then maybe there can be a direct application, right? If we can figure out how to generate and control entanglement in these few-body systems and a prescription for extracting that entanglement, well, then they may be, instead of trying to do everything with logical qubits, maybe we can go straight there and do quantum simulations or quantum sensors straight with the entanglement in our easier to measure and, well, relatively easier to measure and control, high degree of freedom atomic systems. So that's my secret. And here's the future. There's lots of stuff to do. I mean, I think this is, there's a lot of math to do, and I think there's some physics to do too. And I'm very, so thanks to listening to all this, and thanks. I'm at an undergraduate institution only, and I've had a lot of students who've helped me with this. None of them have gone on in physics. So I won't give you their names. Phil Johnson, though, who will be here later, is a colleague of mine at AU who I've discussed a lot of this with numerous times. And so thanks to Phil Johnson, thanks to the organizers at INT, and a little bit of funding. So thanks.
Questions?
Can we go back to the picture of the four-particle points? I just want to kind of stare at that.
Of the
The spheres. that show-
all the way back with the, ooh,
Yeah, this one.
this one, you like that one?
Yeah, I mean, I think I'd produced this picture for lambda equals 0 before, just to identify where the coincidence planes were. And I struggled for a while to find a way to solve the general Schrodinger, not at unitarity, but just at for arbitrary scattering length, in this funny shaped wedge.
Right.
And yeah, I'm going to have to open the book on that again, but maybe we can talk a little bit later about what possibilities there are, and what the most efficient way to impose the boundary conditions.
Right, right,
Problem.
right. I mean, it is a curved sector, right?
Yeah.
So it's not obvious immediately, like, do you want to actually put in a metric or something into your Schrodinger equation to take into account the curvature, right? And do it as, that sounds awful.
Yeah, or if I can diagonalize part of the Hamiltonian first and do it adiabatically.
Well, what I want to do is so if that's my ground state with no interactions, and the symmetrized version of this is my ground state with no interactions, I want to take this times A plus this times B and use a variational method, and that should give me I think it gives you a pretty nice tight upper bound for this should work pretty nicely for a lot of the ground states. Because you can calculate the matrix elements between the symmetrized version of this and this, it's not 0. Right? And so you could imagine using a variational method to connect the two adiabatic states, and then the the right superposition of these should depend on G.
So you might want to look at a paper by Peter Schmelcher's book that appeared in PRL a couple of years ago, where they used the variation and ansatz for the few bosons.
Say the name again?
Schmelcher?
Yeah, Schmelcher and Bruzos.
Yeah.
Yeah, they do something very similar there. They aren't using the exact unitary ones, but that's exactly the method I want to do, but just maybe with a slightly better unitary limit.
You need to include more states in order to get a better accuracy? What's the next one include?
So you mean, in other words, if I want to do a variational method with more states?
Yeah. What's the next stage?
So the next state I would want to do is I would add in the lambda, in terms of energy, the next state is lambda 0 n rho 1. And so that's the next one. And then if I go up to x max 4, I have to add in lambda 4 and another one of those. So it actually scales pretty nicely, right? I mean, to get up to a total internal excitation of 4, I only have to add 4 states out of the, really it should be 5 plus 6 divided by 2. So it's 5 times 6 divided by 2. That's called 15.
The eigenstate in each one of those regions is a spherical harmonic with non-integer quantum number.
Say that again?
Should the eigenstate in each of those regions be because it's free?
Right. Yeah. I mean, these are just linear combinations of spherical harmonics.
Right. So, but the actual eigenstate, I mean, in a sense, I could think of the solution as being a spherical harmonic, except with non-zero. With non-integer L and M possibly.
I mean, I know those exist. I only know from Griffiths that don't normalize well.
So, right, yeah. So, but I mean, ideally, what I would like, what I tried to find before, was an equation, some kind of transcendental equation for those
right.
non-integer.
Yeah. It seems reasonable. It really seems reasonable, and I actually don't know whether the one-dimensional problem, so the one-dimensional problem without the harmonic trap, that's integrable, right? That's what Lieb-Liniger beta-ansatz is all about. That is integrable. I don't know when you add the quadratic potential technically whether that's integrable or not. I mean, I seem to be able to uniquely identify all of the lines, but if it is, that seems to say that something like that should work. At least that's my naive intuition, that if I can find, if this is integrable, then I should be able to find a transcendental equation, right? And we know it works for 2 particles.
That's kind of the Fedorov-Jensen approach, right? I mean, they get Jacobi polynomials, which aren't polynomials, but
For 3.
yeah. But I think you have to go beyond 3.
No, but there's this. I never saw for 4 particles, which is the case here. And
Yeah, for 4 maybe. It's not separable in the hyperangles, so maybe a mess.
because for 3 particles you can go 1D, 2D, 3D, and I don't know what's going on with 4.
And definitely 4 particles has a more, so in the symmetry, the way I keep looking at it is it's more complicated. It's clearly more complicated group than S3. I mean, there's all sorts of technical names for all the ways it's more complicated. And so I'm always fascinated by, so if this, you're saying it works for S3, it works for 3 particles in 1, 2, and 3 dimensions, you can do something like what you're describing?
I tried, I couldn't get it to work.
No, for 3 particles.
Yeah, for 3.
For 3, so it works for 3.
Yeah.
So please send me those references so I can understand exactly what you're talking about, because I'd like to see whether, right, because if I can recast those methods in this language, then I can see maybe how to do it with 4 or why it fails with 4. Right, I mean, that's the hope. Now again, that kind of math begins to be rather technical, right? And if you thought that was, right, so this, right, so I don't know, at the very least, it could be, I might know enough to be able to phrase the question to someone who knew how to solve the math, right? And that can sometimes be all you need to do.
Yeah, maybe if we have other questions, then we can talk in the afternoon. So if you want to join the dinner, you raise your hand. 1, 2, 3, 4, 5, 6. Okay.
Are you counting yourself?
5, 6, 7.
How about you sort of write down names so that you have some evidence and you know who to look for at the end?
I could turn this off now, right?
Okay, yeah. Yeah, so maybe I can